Good morning, everyone. I'm Yumeng, a Joint P student from SASTEC and Hong Kong UST. It's a great honor standing here to introduce our recent work to you, compact gallium nitride-based optical force sensors with hemispherical reflectors. This is my presentation outline. I will start the background of force sensor first, and next is introduction of our design, including device fabrication, sensing principle, and experiment results. As we all know, force sensor measure applied force and convert into readable signals. This signal have been widely used in many areas, like robotics, biomechanical, industrial automation, and healthcare. For example, the force sensor can be integrated in a glove to capture the movement of hand, which can be used to control the robotic hand or enhance virtual reality. In healthcare, force sensor can be attached on the human body to monitor the physiological signals and body condition in real time. Due to the importance of force sensing, various methods have been developed, including pyroresistive, piezoelectric, inductive, and capacitive types. This sensor uses advanced materials like PDMS with carbon nanotubes, response polymer PDVDF, and the GDA dielectric layer. Each has their own strengths. But recently, optical method has gained significant attention due to their unique advantages. Optical force sensor, like FPG, optical waveguide, vision-based system, has detected the changes in the light reflection, refraction, or transmission caused by the force-induced deformation. These sensors are highly sensitive and can provide reliable detection in some challenging environments like high temperature. However, traditional optical force sensing systems tend to be bulky and require the assembly of the individual optical components. It limited their potential for the further miniaturization. And with the advancement in the technology, the sensors are increasing to be smaller in size, offer high resolution, and remain cost-effective. Some people have proposed on-chip integration to solve this problem by integrating different optical components on a tiny chip to enhance their performance. It does have several advantages, like reduce the footprint and reduce the power consumption. But there is still a challenge for large-scale fabrication, since it may be very expensive. Gallium nitride is a material which has been widely used in the optical device like LEDs and PDs due to their unique advantages, such as high efficiency and faster response time. So we propose the monolithic integration, enabling the LED and the PD with the same structure to be integrated the same substrate. This is further proved by the spectral overlap here. The PD green one can absorb the light emitted from the on-chip LED. This is the base stone of the gallium nitride device, work as a sensor. Here comes the detailed fabrication process of the gallium nitride device. It starts with the undoped gallium nitride layer, N-type gallium nitride layer, multi-quantum well, P-type gallium nitride layer for each sulfur substrate through MOCVD. Then the LED and the PD area will be defined and fabricated through the photolithography and ICP edge. Then the ITO layer will be deposited on that for current spreading. Next, the electrodes will be patterned on the gallium nitride layer. A passivation layer and a DBR layer will be deposited through PCVD and the optical coder, respectively. Following is the exposure of the electrodes. Then metal pads will be deposited on that. After lamping and polishing the sulfur substrate, the whole wafer will be cut into individual units. Here shows the optical image of the gallium nitride device in this work. We can see the circle one in the center work as a LED, and the surrounding part work as a PD. Here comes the optical size of the sensor compared with the coin size. The whole sensor chip size is 2.1 millimeter square. After fabrication, the whole chip will be flip chip bonded on the PCB. We may notice that the whole chip is rigid, which is difficult to respond to the force changes. To address this problem, we add a flexible frame on the chip, creating a force sensing system that detects not only the force magnitude, but also its angle position. Here shows the exposed view of the force sensor. The flexible film is made of the PDMS with a white calcium carbonate powder to enhance its light reflection. Since you know the PDMS is transparent, and the whole film is fabricated through the low-cost modeling process as shown here, and with the size and the thickness can be controlled by the molds. Here shows the optical image of the film fixed on the chip. Here comes the sensing principle. When there is no force due to the PD placed equidistantly around the LED, so the initial photocurrent generated by each PD is the same at first. When a central force is applied, the film is more closer to the chip and increasing the light reflection to all the PDs. But when an off-center force is applied, there is more deformation at the press point, so it increases the light reflects more to the nearest PD. For characterization, we first conduct the electrical and optical characterization of gallium nitride device. The first figure shows the IV curve of the LED, which has a forward voltage of 2.3 volt and a resistance of 18 ohm based on the slope of the curve. The inset shows the linear relationship between the light of power and the driving current of the LED. The second figure shows the spectral response of the LED and the PD, where there is an overlap about 30 nanometers. And the third figure shows the IV curve of the PD. We may notice that at the dark condition, the photocurrent is about 10 to minus 9. When the driving current of the LED increases to 5 milliampere, the photocurrent also increases significantly to 10 to minus 5, which shows a high response of the PD to the LED. The last figure shows a linear relationship between the photocurrent and the driving current of the LED. For characterization of force sensor, we put the sensor on a position stage, and the LED is driving at 5 milliampere, and a force gauge was used to press the film. The response will be collected by data collectors. A detectable force distribution is investigated first. The relationship between the force and the photocurrent change across the film is shown in the middle. We may notice that when the distance is 1 millimeter, the sensor reached the best response. So later we choose this point as to characterize our sensor. These two figures on the left shows the measurement range of the sensor and the dynamic response of the sensor in the instantaneous force changes. Some other performance are also investigated. The first figure shows the detection limit by a current by a clear step of 3 millinewtons. The second figure shows the response time and the recovery time of the sensor are 56 milliseconds and 60 milliseconds respectively. The next two figures shows the resolution of the sensor in the loading and unloading process. The last figure shows that the sensor can remain stable for more than 1800 cycle tests. Here comes the force angle position detect. We put the sensor on a rotation stage, and 1 Newton force was applied in the 10-degree steps. The relevant results are shown here. At 0 point, at 0 degree, the force was applied directly on the PD1. So PD1 generated the maximum value here, and as the stage rotates, the value gradually decreases and reaches the lowest point at about 180 degrees, since it's further east to the press point. This is the same pattern will be observed in other PDs. According to the differential photocurrent response, we can use it to detect the force location detection. Here shows the detail information. We divided the whole sensor into eight areas. Each area will have its own digital code. Here shows the response analog output. And for example, at the 0 degree, the dark blue curve reaches the highest value here. And we converted the photocurrent into voltage by the GIA. The dark blue one also remains the highest value. And we may choose this point as a change point. The value exists at this point. We may regard it as the binary code 1. Others may regard it binary code 0. So 0 degree will be translated to 1000. The other error is similar, and the results will be wirelessly transmitted to the user interface. And here is a video shows the process. This is a summary table. The proposed gallium nitride force sensors features compact size and low detect limitation and high resolution. In summary, we have successfully fabricated a gallium nitride optoelectronic device with hemispherical reflector for force sensing. I would like to thank my supervisors and all my group members for the support in this work. That's the end of my presentation. Thank you.